capacitances and how we calculate the capacitances and resistances. Okay, so first of all, so all the MOS transistors or MOS layers. So all the MOS layers includes some metal layers, polysilicon layers, and diffusion layer, substrate. So all these things, so will offer some point of resistances and some capacitances. Okay, and these resistance and capacitance is going to contribute for the overall delay of the circuits and delay of the transistors or something, whatever the delay that we are going to study in the next session. Okay, so here, so the delay is contributed by R and C values. So that R and C is in turn will have provided by so many layers, and we'll be discussing that. So here, so when we want to go for estimating any resistance of any material, so we have used in your labs where you are having some multimeter and you are checking out for resistance of some whatever resistors you are having, right? You have some two terminals will be there and go to check for it. What is the resistance of that material, right? By probing them, right? So when you go for the integrated circuits, so everything will be in very minute nanometer scale in that type. So how you are going to estimate the resistance of certain layers? Okay, so there are so many running will be there for a few millimeters or few nanometers of wire will be there, of polysilicon wire, metal wire will be there. And how you are going to estimate there the resistance of that particular material of particular length? So that is the big question. So how do we estimate that? Okay, so for that reason, so we are going to find out how we can just try to estimate the resistance and how we can try to estimate the capacitances of these different layers. Okay, so first of all, so every layer will have certain resistances and certain capacitances. So they also have inductance also, but that is quite negligible, so trying to neglect that for time being. Okay, and these resistance and capacitance together, they're going to give some delay. So that delay model we're going to study in the next further sessions. Okay, so right now in this session we're going to learn about resistance estimation and capacitance estimations. Okay, right, so here we are going to study a concept of sheet resistance. So where using sheet resistance we are going to find out the actual resistance of the layer. Okay, and similarly we'll have the concept of standard unit of gate capacitance. Okay, so when you go for delays, so these delays again, as said before, are associated with wiring also, it is associated with inverters also, and some other circuitry parameters. So that will be evaluated in terms of delay unit. So we have tau. So this I will try to cover this one in next video. Okay. So overall, the simple thing is, so we have different layers. So polysilicon, metal, or whatever other layers are there. So all these layers are going to offer some resistance, and they'll offer some capacitance. So this is what we need to know. And the next thing, so we can just try to consider a rectangular slab here. Okay, so of some conducting material, so of certain length. So the certain length, so it may be of certain length L, it may be of certain width of W, and it has a thickness of T. Okay, so in this case, how do we estimate the, so we are trying to probe point A and point B, where I am going to measure the resistance from here to here. Okay, probing the, say it may be a multimeter or whatever. Okay, right, so two opposite faces. So this is the characteristics. So any material, conducting material, if I am taking a conductor rectangular slab, it has a different parameters I can see. So one thing is it has a dimensions, that is L, it has some W, it has some thickness T. At the same time we have some other parameter or characteristics called resistivity. So this resistivity is actually going to vary from different materials. So different materials will have different resistivity. Okay, so metal will have, in that again metals, aluminum will have certain resistivity, and copper will have some other resistivity, like that. So we have different materials, and different materials will have different resistivity. So how do we estimate the resistance of these materials? So this you already come across in your lower uh, semesters or in a PU or something like that. So how do you in calculate a resistance of a material? So this you have studied in your physics, right? So rho L by A. Okay. So rho is your resistivity from point A to point B, whatever the A is there, and L is the length of the material, and area of the material. Okay, so in this case, so this will be your L. So this will be area is nothing but we can take this cross sectional area. So this cross sectional area means we have W is there and W into thickness T. So I can just replace this one as where A is equal to W to T. So I can write our distance between A and B equal to rho L divided by W into T. Okay, right. So now, so we can consider the case of where the length is equal to W. Okay, where length is equal to W. That is we can call as a unit square. Okay, so in that case, so L is equal to W, that will become a square. So in that case, here length and W, L by W will become 1. L by W ratio will become 1. Okay, in that case we are going to left with so rho by T. Okay, so whenever you take unit square, that is when L is equal to W, it may be 1 meter by 1 meter, 1 meter or 1 nanometer into 1 nanometer, whatever things. So where L is equal to W means, that means this LW will become, ratio will become 1. So then resistance AB will become rho by T. Okay, and this rho by T, so when resistance is having, when L is equal to W, in that case, so we call this parameter a new parameter called as sheet resistance. This is your sheet resistance. So sheet resistance is equal to rho by T. Okay, so and it is expressed in terms of so ohms per square, right? So ohms per square. This is your unit you are going to use for sheet resistance. Okay, and so the sheet resistance of different materials are shown here. Okay, so this is a table. It's going to show you for different technologies. So for 5 micrometer process, for orbit 2 micrometer, orbit 1.2 micrometer. Okay, so there for different layers. So for metal layer it will be something like 0.03, okay, ohms per square. So similarly we'll have for n transistor channel 10 to the power of 4, okay, ohms per square. For p transistor channel it is 2.5 into 2 to the power of 4 ohms per square. Okay, so this we are going to use this. So later part I will show you that. Okay, so this is your some table which shows for particular technology the sheet resistance value. Okay, right. So we have some calculations here. So it is a resistance calculation for transistor channel. How do we calculate resistance calculation for any channel of the transistor? Okay. So here the first side we have a minimum size transistor, that is 2 cross 2. Okay. So because the polysilicon diffusion minimum dimension is 2 lambda, right? So this polysilicon is there, the minimum width of 2 lambda, and we have a minimum width of 2 lambda for diffusion here, right? And so this will be a transistor. The channel region is this intersection part, whichever the overlapped part is there. So this is your channel region. Okay, so to find out the resistance for this particular thing, so I need to go for taking the ratio. So what is the length of the channel, what is the width of the channel in this case? Okay, so length is nothing but again 2 lambda, width is also 2 lambda. So L by W ratio will become 2 lambda by 2 lambda, that will become 1 by 1. So yeah, here I'm going to introduce another parameter called Z here. So Z is nothing but a ratio, that is L by W ratio is called as Z. Okay, right. So this Z ratio will become 1 is to 1 or simply 1. Okay, right. So in this case, so for this particular thing, so what will be my uh, resistance? So total resistance we can call it as for if we take for 5 micrometer process. Okay, so for 5 micrometer process, so what will be your n transistor channel resistance? For that, this will be 10 to the power of 4 ohms per square, right? So I can write, so we have one square. So this is only one square where L is equal to W, ratio is 1. Okay, 1, the ratio is 1, so Z is equal to 1. We have something like Z into RS. Okay, so total R is equal to Z into RS, and Z is 1 here, and RS is nothing but your 10 to the power of 4 ohm. Okay, ohm per square actually, right? This is for 5 micrometer process. Okay, so similarly, so this is another example here where we have so length is equal to 8 lambda. So don't get confused here. So this is actually your diffusion part, and this entire thing, this is your poly. So that's why I indicate like this. Okay, you can just see the pattern what I've shown here. for poly and diffusion. So this polysilicon, so this is your 8 lambda. So that means this is one of the terminal, this is another terminal. So from here to here is your length of the channel. Okay, so from here to here will be your width of the channel. So length of the channel will become 8 lambda, it is shown here, and width of the channel is actually your 2 lambda. So total transistor channel is this much. This overlapped region is your transistor channel, and your L by W ratio is 8 lambda divided by 2 lambda. That will come across something like 4 is to 1 ratio. Okay, so it may be again 16 lambda and 4 lambda also, then also the ratio will come to 4 is to 1. Okay, so for this particular example, so what will be my resistance? So for this I can go for R is equal to Z into RS, Z times RS. So what is Z here? Z is actually 4 is to 1, or you can simply take it as 4, or 4 by 1, or 4. So 4 into, what is your sheet resistance for 5 micrometer process for N channel transistor? So it is 10 to the 10 raised to 4, right? It's 10 raised to 4, right? So 10 raised to 4 into 4 times, that is Z. So here Z is 1, so 1 into the power of 4. Here Z is 4, so 4 into the power of 4. Okay, so this is how you calculate the resistance for your transistor channel. Right, so this is another example how to calculate for your resistance for your inverters. So in this case, we are actually calculating on resistance. So when both transistors are on, okay. So or when we have something like static connections, we call it static power dissipations or something like that. Static current. Right. So in this case, we are using a depletion mode transistor here, and the ratio is given as 4 is to 1. L is to W ratio is 4 is to 1. So this ratio, example, it may be 8 lambda into 2 lambda, or it may be 16 lambda into 4 lambda, whatever. So the ratio is 4, and here this pull down transistor, the ratio is 1. 1 is to 1 ratio is there. And when you take the example here, the resistance is given as 10 kilo ohm here. So when you have resistance of the channel here 10 kilo ohm, and since we have 4 times larger here, that is Z is equal to 4 here, you can take it as 10 times 10 into 4. So then become 40k. Okay, 40 kilo ohm, right? So the total overall resistance we can calculate Rn is equal to resistance of pull up device and on resistance of pull down network, and it is nothing but 40k plus 10k, that will be 50k. Okay, so this is again we can have the more resistance is going to be there, and that means there is static power dissipation will be there. So because this is also on, this is also on in that case, so there is a resistance from VDD to VSS, so we can take it as a 50 kilo ohm, right? So similarly, this is not a proper way, again there is a static power dissipation in this case. So for CMOS inverter, so you can take this for MOS ratio is 1 is to 1, and for PMOS also we are taking as resistance 1 is to 1. So here Z again, Z for pull down is also 1, Z for pull up is also 1 is to 1, means 1. Okay, so both are same dimensions, but when you go for here, the resistance RSN is 10 kilo ohm, and RSP is 25 kilo ohm. So why 25 kilo ohm means, because we can say that is your P channel is different, 2.5 into the power of 4, and something like 2.5 times the N channel, right? You can take in that case. So if for N transistor channel 10 to the power of 4, for P transistor 2.5 times of N transistor channel. So that means you can just simply take. So if this is 10k, so the resistance offered for same 1 is to 1 transistor of PMOS, so you can divide 2.5 into 10 to the power 25k. So the overall the inverter resistance or on resistance we can given by, so summation of these two things we'll get as 35 kilo ohm, right? Okay, this is about your resistance. So this is the thing. So while estimating the something like um, while estimating the lengthier layers, so we can just take, we can divide, say we have this slab is there, the layer is there, and if I want to calculate the resistance for this, so I can simply divide this into unit square. Okay, so if you just divide this one like this, okay, so this is something like L equals W. So this is your L is equal to W. Okay, this is a square. So for this square we call as RS. Okay, and we know RS. So for particular technology we can calculate resistance RS easily. Okay, so once we know the actual length of the uh, conductor what we are using, okay, we can just count how many times we can just divide in terms of uh, L is to W. Okay, so if you just look at one, it is one means, so we can just 1 unit, 1 unit, 1 unit, we can just make that, so multiple of that. So how many square is going to fit here? This is what we can call as a Z here. So we have 1 2 3 4 5 6. So now I can easily estimate the resistance offered by this particular length of layer as 1 2 3 4 5 6, 6 times the sheet resistance RS. So this is how we can estimate the resistance of the material. Okay, right. So this is the thing, and next we'll go for capacitance. Okay, so each layer of your transistors, so will offer some capacitances. So there are something like parallel plate capacitance effect. So this we already discussed in the module 1, where we have accumulation region, depletion region, something like that. Okay, so similar to that we'll have an effect of parallel plate capacitance effect, so where we have different layers. So in between we have silicon dioxide. Okay, so we can take an example of, say we have okay, so one layer is there here, so it may metal layer, and we'll have some another layer is called polysilicon layer or something like substrate layer. So if this is the metal, in between here we have silicon dioxide, between here again we have silicon dioxide. So that means, so this is a conductor here, this is also a conductor here, and between that we have a dielectric material here, silicon dioxide insulator, so that acts as a parallel plate capacitor. So that already studied parallel plate capacitor effect, so that will contribute some from capacitance from here to here. And so we calculate from, so metal to substrate will have some capacitance, and we'll have something like polysilicon to substrate will have some capacitance, so there will be capacitance effect. Okay, and this capacitance effect we already know the uh, so equation for that, how do you calculate the uh, capacitance of any material? So that is nothing but epsilon A by D. So this you already know this equation. So epsilon is the permittivity, so where epsilon is equal to epsilon naught into epsilon of the insulator. So epsilon is the permittivity of free space, and epsilon of insulator is what insulator you are using, in this case silicon dioxide. So silicon dioxide permittivity I have to take. So A is the area of the parallel plate capacitor, and D is the distance between the or two parallel plates or thickness of the silicon dioxide. So this is how we calculate the capacitance here. So similarly, so in this case, as I said before, we'll have a difference table here. Okay, so this is again for some particular technology. Okay, so for my 5 micrometer process. So here the table, the gate to channel capacitance, so is given as 4 into 10 to the power of minus 4 micrometer square. Okay, okay, so similarly we have for diffusion for as 1 into 10 to the power of minus 4. So polysilicon to substrate we have 0.4, so metal 1 to substrate as 0.3, metal 2 to substrate as 0.4, metal 2 to metal 1 as zero point 0.4, metal 2 to poly as 0.3. So these are the different values for taken as example for particular technology. And whatever you're seeing in the bracket, so this the uh, numbers you're seeing in the bracket is nothing but we call as a relative value. So this is actually calculated by, so the specified value divided by gate to channel value for that particular technology. Okay, so this we'll see that, so we are going to use this for calculating some example. Okay, so this is specified value divided by the minimum gate to channel value of that particular technology, right? So you can remember, so here we have a concept of standard unit of gate capacitance. So we can define this as a gate to channel capacitance of a MOS transistor using, sorry, having W is equal to L is equal to feature size. So when you have a minimum feature size transistor, so what is the actual gate to channel capacitance is there? So that we call as a standard unit of gate capacitance. Okay, standard unit of gate capacitance. So that means we have a polysilicon here. Okay, and so you have these two substrate, so n region and n region, source and substrate. So whatever the area is there here, okay, so below this, so it having something like minimum dimension L, okay, L and W, okay, right, 2 lambda 2 lambda whatever. So whatever the capacitance you're going to get, so that is from this gate to this channel region, so this capacitance, so we call as a standard unit of gate capacitance. Okay, right, so this is one thing. This is for actually we can calculate for 5 micrometer. This is actually denoted by square of Cg. So standard unit of gate capacitance denoted by this symbol is square of Cg here. Okay, so for 5 micrometer process, so we can calculate the area per standard square as, so 5 micrometer into 5 micrometer, that will be equal 25 micrometer square. Okay, so how, why 5 micrometer into 5 micrometer? Because the length of the channel is minimum, right? So what is minimum size length of the channel? It will be uh, 2 lambda, right? So what is lambda? So lambda is equal to feature size by 2. So that I already discussed it, right? So feature size is 5 micrometer divided by 2 is 2.5 micrometer. Again 2 lambda means 2 into 2.5 micrometer, it comes again for 5 micrometer. So length will be 5 micrometer, width will be 5 micrometer, total area of the gate to channel area, what we are going to see as 25 micrometer square. So the capacitance value is something like gate to channel is 4 to the power of minus 4. So this you can see from your channel, sorry, table. So gate to channel is 4, right? So 4 into, so whatever the area is there, 10 to the power of minus 4 picofarad per micrometer square. And standard value for this particular technology, okay, that will be equal to standard unit of gate capacity is equal to 25 micrometer square into this actual CGU, that is 4 into 10 to the power of minus 4 picofarad per micrometer square, that you are going to end up with 0.01 picofarad. So this will be your standard unit of gate capacitance for 5 micrometer technology. So same thing it is for if you are taking for 2 micrometer technology, then you should take 2 micrometer and 2 micrometer, that will become 4 micrometer square. So then you are going to take is 4 here, 4 into 4 you're going to calculate, you're going to end up with some other value that will be standard unit of gate capacitance for that particular 2 micrometer process. Okay, so why this is necessary means because, so when you calculate the different capacitance in the other layers, so while doing that layers calculations, you are going to express your capacitance in terms of standard unit of gate capacitance. So that may example, so what is the value of capacitance for this particular metal layer to some another layer? So you will say something like 7.15 into square of Cg. It's like that. Okay. So the square of Cg as again depends on different technology or different process. Okay. So once you for different process we can easily calculate the particular layer capacitance values. Okay. So this will know how it's some example here. Okay. How do we calculate the capacitance? So we have some example here, some area capacitance calculations. So assume this is the layer we are having already. So some length and some W, length of 20 lambda and width of 3 lambda. Okay, so first thing is we will take relative area first. So relative area, if we consider this as a uh, relative on layer. So and the previous slide I showed you, relative area is equal to, so we have in this slide, right? Sorry, here we are having, right? So this one, so relative value equals specified value divided by gate to channel value of that technology. Okay, so that you are going to perform here. So relative area is nothing but what is the length, actual length of this layer L, it is 20 lambda. What is the width? 3 lambda. So the relative area of this particular layer is 20 lambda into 3 lambda. That's your value divided by what is the minimum gate to channel value, that will be your 2 lambda into 2 lambda, that is the minimum feature size, right? Channel 1 gate to channel, so it will give 4 lambda square or 2 lambda and 2 lambda. So just solve it, you are going to get the value as relative area as 15. So once you get 15, this relative area, if we consider this layer as a metal, so what will be the capacitance for metal to substrate? Okay, if we consider this a metal, capacitance to substrate from metal to substrate will be relative area into relative C value. So this is where I'm going to use relative C value here. Okay. So in the previous tabulation we saw, right, the relative values. So metal 1 to substrate, we have the relative value as 0.075. Remember that, right? So now, so 0.075 relative area is 15 as I got here. And what is the relative C value for that particular 5 micrometer process? It is for M1 to substrate, we have 0.0750 times of Cg. So we just use multiply this. So the actual value will be, if this is a metal, the capacitance will be 1.125 times of standard unit of gate capacitance. Okay. So if the same layer, if it is a polysilicon, so then the relative area into relative C value of polysilicon to substrate. So polysilicon to substrate relative C value is 0.1. So this you can just see here. So polysilicon to substrate, the relative C value is 0.1. Okay, so I'm going to replace that, right? Okay, so 15 into zero point 0.1 times of standard gate of unit of gate capacitance, that is going to 1.5 terms of Cg here. So similarly, you will go for capacitance substrate. So you'll replace this with n type of division 0.25. This again you can see in your tabulation. Okay, right. So what exactly this 1.125 means? So it means the defined area in metal has a capacitance to substrate 1.125 times of the standard value of gate capacitance. Okay, that's the actual meaning. Okay, so we have some another example here. So we'll see this. So this is one of the layers you are given. So we have some metal layer is there, we have some contact is there, and we have some transistor is there, and here they are given some dimensions. So they asked us to calculate the capacitance of each layer. Okay, so how do we calculate each layer capacitance? So we have done it previously, right? So just before we did, we'll calculate the relative area of the metal. The relative area is actually of the metal is, the layer length is, for metal it is 100 lambda into 3 lambda. So metal area is 100 lambda into 3 lambda divided by standard gate area is 4 lambda. So that is 2 lambda into 2 lambda is nothing but 4 lambda square. So you are going to get the value of 75. Okay, right. So how to calculate metal capacitance? So metal capacitance is nothing but this 75 relative value into relative C value. So relative C value for 5 micrometers, previously in the last slide we have done 0.075, right? So 75 into 0.075, that becomes 5.625 into times of standard unit of gate capacitance. So this will be your from this metal layer capacitance. So now we consider the polysilicon area. So we are excluding the gate region. Okay, we are not including the gate region. Okay, so polysilicon area is actually here taken as 4 lambda into 4 lambda. So why 4 lambda into 4 lambda means, so we are using contact here, right? So we are using contact here. So this contact area concludes having uh, two layers. One will be metal, will be focused for in the first floor, and similarly we will have in the ground floor something like 4x4 polysilicon will be there. So that 4x4 polysilicon will be extended here into like this, in this fashion. So this, if you understand, you have seen the my previous videos, you would understand easily this why I'm taking this one. Okay, you can just go back to this video where I have taken the microband example using that tool. So polysilicon is 4 lambda into 4 lambda, one thing, plus we have here this one, this is 1 lambda is there, and from here to here 2 lambda is there. So 2 lambda plus 1 lambda, that will becomes 3 lambda. So 3 lambda into this minimum dimension is 2 lambda. So 3 lambda here, 2 lambda here, so that will be dimension, and 4 lambda, 4 lambda. So total will be 22 lambda square, and this will be should be divided by 4 lambda square. Okay, to get standard this ratio. So 22 lambda square divided by 4 lambda square. So lambda square cancel. So you are left with 22 divided by 4 into the relative value of uh, polysilicon to substrate will be 0.1. You can see through the table. Okay, that will be end up with 0.55 times of standard unit of gate capacitance Cg. So similarly, for actual this gate, this will be unit dimension 1 times of Cg. Why I am taking 1 times of Cg means, So this gate capacitance minimum dimension is there, that's exactly equal to this Cg. So total capacitance offered from different layers here, we can take it as, so Cm from metal plus polysilicon capacitance plus gate capacitance, that is your 5.625 plus 0.55 plus 1. So that will end up with 7.20 times of standard unit of gate capacitance. Okay, so this is about how you calculate your capacitance. Okay, right. So this will be enough for this session. So we'll continue uh, the next session with the delay unit. Okay, so thank you.